Hey Stats, I'm going to go over the two progress check FRQs that I assigned in week 4. So one was from Unit 6 and then the other was from Unit 1. So I'm going to start with the Unit 6 progress check FRQ. So question 1 says a recent survey collected information on television viewing habits from a random sample of 1,000 people in the United States. Of those sampled, 37% indicated that their favorite sport to watch on television was American football. We want to construct and interpret a confidence interval for the proportion of all people in the United States who would indicate that their favorite sport to watch on television is American football. So the first thing I'm going to do, we're going to go through our state plan, do, conclude steps. So I'm going to state what it is I'm looking for. I want first thing I'm going to do is state what P is, and that's the true proportion of people in the U.S. who prefer football. And I want to construct a one sample Z interval for P. We're going to do that at 95% confidence. Okay, so there we go. Now we're going to plan. So this is where we're going to check our conditions. Random. And I think they do a recent survey collected information on from a random sample. So sample stated as such. Um, 10%. And they collected a sample of 1,000 people. 1,000 times 10 is 10,000. So I would say US pop greater than 10,000. And then large counts. And so in this case, they give us a p hat value of 0.37. So we're going to multiply n times p hat. So 1,000 times 0.37 is definitely greater than 10. That would be 370. And 1,000 times 1 minus that, which would be 0.63, also greater than 10. So we're good. We're ready to construct our one sample Z interval for P at 95% confidence. So we could do this by hand. I prefer not to. I'd like you guys to use your calculators for this. So I'm going to pull up my TI-84. We're going to do stat, tests, and we want a one prop Z interval. Oops, there it is. So one prop Z int, and it'll ask me for some information. Remember that x over n should give you your p hat value. So our p hat value was 0.37. So our n was 1,000. And that means our x has to be 370. So we want x over n to give us 37%. Confidence level 95%. Go ahead and calculate. All right, so 0.34 to about 0.40. Let's go do, whoops. We get an interval where p hat equals 0.37. And what did I say? 0.34 to about 0.40? Yes. 0.34 to 0.40. And so conclude. Right, so we are 95% confident the true proportion of U.S. people who prefer football is between 0.34 and 0.40. So 34, somewhere between 34 to 40% of people. Okay, let's move on to part B. So based on our answer to part A, is it reasonable to believe that 33% is the actual percent of people in the United States? And so what we're going to say is, since 33 is not within our interval goes from 34 to 40, I'm going to say no. So I'm going to say no, 33% falls outside of the 95% confidence interval. All right. Next. Cool, so question 2. A fair die with its faces numbered from 1 to 6 is one on which each number is equally likely to land face up when the die is rolled. On a fair die, the probability that a number 6 will land face up is 1 out of 6. A group of students want to investigate the claim about manipulating a fair die so that it favors one outcome. The claim states that if the fair die is put into an oven at 200 degrees Fahrenheit for 10 minutes, the inside of the die will begin to melt. Then when it cools, the inside will be solid again, but weighed more towards the bottom. This shift in weight will cause the face that was up when the die was cooled to land up more often than the other faces. The students obtain a fair die and bake it according to the preceding directions. The die cooled with the number 6 face up. After the die cooled, they rolled the die 200 times, and the number 6 landed face up 43 times. Let P represent the population proportion of times the number 6 will land face up on the die if the die could be rolled an infinite number of times. Clark, one of the students, constructed a 95% confidence interval for P as 0.215 plus or minus 0.057. Does this interval provide convincing statistical evidence that the number 6 will land face up more often on the baked die than on a fair die? Explain your reasoning. Okay, so if the die is fair, the proportion of 6s that we're going to expect, so I'm just going to do P fair, is 1/6, right? And that as a decimal is about 0.17. I'll say 0.167. So Clark's interval here, let's actually write this in interval notation. So if I do 0.215 minus 0.057, that gives me 0.158. And if I do 0.215 plus 0.057, that gives me 0.272. So any value in that interval is seemingly plausible. Right? So the fact that if the die is fair, we would expect the proportion of sixes to be about 0.167, and that does fall on that interval. We don't have evidence that the baked die will land face up more than a fair die. So I'm going to say no. 0.167 proportion of sixes expected for a fair die falls within Clark's confidence interval. Okay. All right, B. Aurelia, another student, suggested they conduct a significance test to investigate the claim. She tested the null hypothesis p equals 1/6 versus the alternative p is greater than 1/6 at the significance level of 1 or of 0.05. She obtained a result with a p-value of 0.033. Do the results of the significance test agree with the results of Clark's confidence interval in part A? So remember, with a significance test, we're going to compare the p-value that she gets to the significance level, and if the p-value is less than that, we're going to say we have a significant result. In this case, having a significant result, right, tells us to reject H null in favor of HA, since P is less than alpha. So this is saying, remember, the alternative hypothesis is saying that we have evidence that the baked die lands face up more often than 1/6 of the time. So this does not agree with our result in part A. So it does not agree with Clark's result. Okay, so now two standard normal curves are shown below, one for the confidence interval calculated in part A and one for the significance test conducted in part B. For the confidence interval, label the critical values for the 95% confidence level and shade the area that represents the outer 5%. And then for the significance test curve, label the critical value for 5% significance level and shade the area representing the values of Z that would lead to a rejection of the null hypothesis in B. All right, so for the confidence interval, what we want are these critical values such that we capture 95% of the data in the middle, right? That means each one of these needs to be 0.025. So to do this in your calculator, we're going to use inverse norm. And I'm going to do 0.975. We're going to keep the mean 0 and the standard deviation 1 because we're looking at the standard normal distribution. And that tells me 1.96. Right, so the way that shows up is that this one is positive 1.96, and this one is negative 1.96. But for the hypothesis test, this is a one-sided hypothesis test, which means since we set alpha to be 0.5%, sorry, to be 5%, this is 0.05, okay? And so again, I can use inverse norm to get this critical value where all the area to the left of that is 0.95. So I'm going to change that to 0.95. And I get 1.64 as my test statistic. All right. Last part of this first question. So Joaquim, a third student, noted that the confidence interval in part A gives plausible values of the parameter as an interval between two values. He suggested they develop a one-sided confidence interval because they were only concerned with whether the number 6 was landing face up more often than expected, not less often. The one-sided interval will determine a value L such that all plausible values of P are greater than L, and the formula for L is just P hat plus our Z critical value times our standard error. So I want to determine the values of Z critical needed to create a one-sided 95% confidence interval, then calculate the value of L, and then we'll see if Joaquim's one-sided confidence interval agrees with Aurelia's significance test. All right, so for this one-sided confidence interval, this is a little bit more of a in-depth question. Since I still want it to be 95%, I now only want to look at when my values of p hat are larger than 1 out of 6. So I still want it to be 95%, but I want to separate, I want my 95% to be the larger 95%. I want to separate the smaller 95% from the larger 95%. So I'm going to find this Z critical value here. Sorry, the Z critical value here. So we're going to do inverse norm 0.05. But that's going to get us the same thing as inverse norm 0.95. So it's the negative version of this. So negative 1.64. And then they give us the formula, right? We're going to take our p hat value, which is going to be the 43 out of 200. We're now going to add negative 1.645 times the standard error, which would be let's see, 43 out of 200 times the complement to that, which is what, 157 out of 200, and that's all over 200. And that's going to come out to approximately 0.1672. And so what we're saying is that we are 95% confident the true value of P, which is the proportion of sixes that come up, is greater than 0.1672, right, which is greater than 1/6. So this agrees with Aurelia's result.